Start inside the slow tightening of export licensing friction on a critical semiconductor input rather than announcing a geopolitical decision. Cause and effect chain where a minor administrative control gradually turns into defense supply pressure. Gallium as a hidden dependency layer between civilian semiconductor manufacturing and military-grade electronic warfare systems. Mood applied, cold and methodical, restrained, evidence-driven, emotionally flat but structurally tense. There was no single moment where the world woke up and said, China has cut off gallium. That's the first misunderstanding worth clearing. In 2023, what actually changed was far more procedural. Export licensing requirements for gallium and germanium. Not a dramatic shutdown, not a visible blockade, just paperwork getting heavier, approvals taking longer, and shipments moving with less predictability than before. On the surface, that sounds almost boring. Trade bureaucracy rarely makes headlines. But in materials like gallium, boring is exactly where the pressure builds first. Gallium is not a metal most people think about, even in industrial discussions. It doesn't sit in the public imagination the way lithium or copper does, but it sits inside gallium nitride semiconductors, and those are critical for high-frequency, high-efficiency electronics. Radar systems, electronic warfare modules, satellite communication arrays, advanced power switching systems. Not the visible hardware of defense, the performance layer underneath it. And that distinction matters more than it seems. Because when China tightened export licensing, it wasn't just affecting a raw material. It was affecting a node in a layered production system where substitution is not immediate and sometimes not even technically clean. Here's the part that gets missed in most simplified explanations. Gallium isn't mined in a straightforward way. It's largely a byproduct of bauxite and zinc processing. You don't just open a gallium mine the way you would imagine with iron ore or coal. You scale refining infrastructure that already depends on upstream industrial ecosystems. And China, over the past 2 decades, didn't just expand mining capacity, it built dominance in the midstream, separation, purification, and industrial processing at scale. That's the real leverage point. So when licensing rules tighten, the constraint isn't theoretical availability, it's controllable flow. Who gets it, when they get it, and under what administrative conditions. Now connect that to defense manufacturing in the United States. Modern defense systems don't sit neatly inside a single factory. They are distributed across subcontractors, tiered suppliers, and specialty material providers. A radar system might rely on components whose semiconductor base layers depend on gallium nitride substrates sourced through highly specialized supply chains. And those supply chains assume something very specific: predictability, not abundance, predictability. Once that predictability weakens, even slightly, the effect doesn't show up as immediate shortages. It shows up as procurement friction, longer qualification cycles, engineering hesitation around scaling certain designs, small delays that stack quietly across programs already running on tight timelines. China's move, viewed structurally, doesn't need to stop exports entirely to create pressure. It only needs to introduce administrative variability into a system optimized for stability. That's the part that tends to get underweighted in political commentary, because most narratives focus on access versus cutoff. But the more accurate framing is control versus certainty. And certainty is what complex manufacturing systems actually depend on. There's also a historical layer here that matters. China's export controls on strategic materials didn't start with gallium. Rare earth elements were the earlier signal, where processing dominance translated into geopolitical leverage during earlier trade tensions. Gallium and germanium sit in the same conceptual category, even if the end-use applications differ. The pattern is consistent. Dominance is not built at the resource level, but at the processing bottleneck level. And once that bottleneck exists, policy tools like licensing become effective without needing outright bans. So when people describe this as a ban, it misses the mechanism. The system doesn't require prohibition, it requires discretion. And discretion is harder to model than restriction. At this point, a more uncomfortable question emerges, not about China's decision itself, but about exposure elsewhere. If advanced defense electronics depend on inputs concentrated in a single refining ecosystem, then the risk isn't just supply disruption. It's structural dependency embedded deep inside industrial design choices made years ago. That's where the real tension begins to form, even if it's not visible in headlines yet. Opening approach. Continue from procurement friction and shift into how defense systems quietly reprice risk when a single material stops being stable in assumption models. Escalation from component dependency to system-level redesign pressure to strategic procurement recalibration. Unique angle. Gallium's real impact is not supply disruption, but forcing defense institutions to reevaluate whether their entire electronics architecture assumptions are still valid. Mood applied. Cold and methodical. Denser analysis, slightly more technical layering, still emotionally restrained. The strange thing about supply chain risk is that it rarely announces itself as risk. It shows up as accounting adjustments first, longer procurement horizons, revised supplier scoring models, internal notes about supply chain uncertainty factors being added into contract evaluation frameworks. None of it looks dramatic in isolation. Put together, it signals something more structural. The system is starting to price instability into its own assumptions. Gallium doesn't need to disappear from global markets for that process to begin. It only needs to become less predictable as a flow. And predictability in defense electronics is not a luxury variable. It is embedded in how platforms are certified, tested, and scaled. Take gallium nitride, GaN systems again. These are not experimental technologies anymore. They are already embedded in modern radar arrays, electronic warfare suites, and advanced communication systems. What matters here is not just performance, but reproducibility at industrial scale. Because defense systems are not built once, they are replicated across production batches, sometimes over decades. If the underlying semiconductor supply becomes uncertain, not absent, but administratively variable, the procurement logic starts shifting from optimization to insurance. That shift is subtle, but measurable. You see it in increased dual sourcing strategies. You see it in governments funding parallel supply chains that are economically redundant in the short term. And you see it in contractors reworking qualification pipelines so they can swap suppliers without restarting entire certification cycles. But there's a catch that complicates all of this. In gallium-based systems, substitution is not purely a sourcing problem. It is an engineering constraint. Alternative semiconductor materials exist, but they are not drop-in replacements. Silicon carbide, for example, plays a role in high-power electronics, but it does not replicate gallium nitride's performance envelope cleanly in every use case. That means substitution is not symmetrical. You gain in one area, you lose in another. So the system doesn't switch, it bifurcates. Some applications get redesigned around alternatives. Others stay locked into gallium-dependent architectures because the performance trade-offs are too significant to accept in critical systems. This creates a split architecture inside defense procurement. One layer trying to decouple from constrained materials, another layer still structurally dependent on them. And that split is expensive. Not just financially, but in coordination terms. More suppliers, more testing pipelines, more certification branches, each one adding time and reducing agility. There's a historical echo here that matters, even if it's not identical. When rare earth export restrictions tightened in earlier cycles, industries didn't immediately collapse or relocate. Instead, they built parallel sourcing systems, often inefficient, often redundant, just to reduce exposure to a single dominant processing hub. Gallium is following a similar structural path, but in a more sensitive domain, high-frequency defense electronics, and that sensitivity changes the stakes. Because when rare earths were constrained, the pressure was largely industrial and commercial. When gallium tightens, even marginally, it touches systems tied directly to military capability timelines. Which brings us back to China's export licensing mechanism. The key point is not prohibition. It is administrative control over flow timing. That sounds technical, but in supply chains, timing is often equivalent to control. A 2-month delay in a semiconductor input doesn't just delay production. It can cascade into contract renegotiations, schedule shifts, and in some cases, redesign decisions if the delay aligns with critical procurement windows. So the system reacts preemptively, not because shortages have fully materialized, but because uncertainty has crossed a threshold where it becomes rational to assume future friction. And that is where policy and engineering begin to interact in uncomfortable ways. Because engineers want stability, policymakers are now forced to assume variability. Those two logics don't align cleanly. At this stage, I find myself questioning whether the current wave of supply chain resilience strategies is actually building resilience, or simply redistributing fragility across more nodes. It feels safer on paper. It rarely feels simpler in execution. And the direction of travel is clear enough, even if the end state isn't. More duplication, more parallel sourcing, and more internal redesign work done just to preserve continuity assumptions that used to be taken for granted. Efforts to reduce dependency are actually increasing system complexity and hidden fragility. Unintentionally create new bottlenecks and delays. Resilience policies in critical minerals often behave like risk displacement rather than risk removal, especially for gallium-linked semiconductor chains. Slightly more critical tone, denser causal reasoning, controlled skepticism. There's a contradiction that starts to show up once you follow gallium far enough into defense planning. Every official response to material dependency sounds like a step toward resilience. Diversify supply, build domestic capacity, fund alternative processing, create strategic reserves. On paper, it looks like risk reduction. But in practice, what often happens first is risk redistribution. Because gallium doesn't sit at the top of a simple supply chain, it sits inside a nested industrial stack: bauxite processing, zinc refining, chemical separation, high purity refinement, then semiconductor fabrication. Each layer introduces its own geography, its own cost curve, and its own bottleneck. So when governments and firms respond to China's tightening export licensing by diversifying, they are not replacing a single node. They are rebuilding an entire chain in parallel. That's slow, expensive, and uneven. Take the United States as an example. Domestic initiatives around critical minerals and semiconductor supply chains have increased significantly since the early 2020s, including funding under the CHIPS and Science Act framework. But gallium specifically is not just a mining problem, it is a midstream refining problem. And midstream capacity is where most countries are structurally weakest, because mining is visible, fabrication is strategic. Refining sits in between, industrial, capital-intensive, and often environmentally constrained. It doesn't attract the same political urgency until something downstream starts to strain. So what happens instead is partial rebuilding, a bit of domestic extraction attempts, some allied sourcing, some recycling programs, some stockpiling. Each one adds redundancy, but also adds coordination overhead. And coordination overhead is where complexity becomes its own constraint. Now here's where gallium becomes interesting in a more technical sense. Global gallium production is relatively small compared to bulk industrial metals, but its importance is disproportionate because it feeds high-performance semiconductor applications. That mismatch, low volume, high strategic value, is exactly what makes it sensitive to administrative controls like export licensing. When China adjusts licensing timelines, it doesn't need to alter total global output dramatically to create behavioral changes elsewhere. It only needs to introduce uncertainty into delivery schedules. And uncertainty changes procurement behavior faster than price does in some cases. This is where defense contractors start adjusting assumptions in ways that are not always visible externally. Multi-sourcing becomes default rather than exception. Inventory buffers increase. Contracts include more clauses for supply variability. But each of those responses carries cost. Inventory buffers tie up capital, Multi-sourcing increases qualification burden. Contractual flexibility reduces efficiency. So resilience is not free. It is paid for in reduced optimization. There's also a quieter effect that doesn't always get discussed: design conservatism. When engineers cannot fully trust long-term material availability, they tend to avoid aggressive dependency on a single advanced material pathway in future designs. That means some systems that could benefit from gallium nitride performance might instead be designed with fallback architectures in mind from the beginning. In other words, performance potential gets partially constrained by supply chain psychology. That is a subtle but real shift, and it feeds back into industrial strategy. Because if enough programs begin designing around uncertainty rather than optimal materials, then the demand signal for next-generation gallium-based systems becomes less stable. That affects investment decisions in refining, fabrication, and upstream production. So the system starts to loop back on itself, not through collapse, through hesitation. There is also a geopolitical layer here that cannot be ignored. China's position in gallium processing did not emerge accidentally. It is the result of long-term industrial policy that concentrated midstream capabilities where environmental and cost advantages aligned with scale. That creates leverage not because China controls the entire market in a simplistic sense, but because it occupies enough of the processing layer to make timing and approval mechanisms meaningful. And timing, again, is the critical variable. At this point, I find the most important question is not whether alternative supply chains can be built. Technically, they can. The question is whether they can be built fast enough to match the speed at which dependency is now being repriced into defense planning systems. Because those two speeds, industrial build-out versus strategic risk adjustment, are not synchronized. And when they diverge, you don't get a clean break. You get a prolonged period where every decision is made under partial uncertainty, with institutions gradually adjusting without fully acknowledging the shift in baseline assumptions. That is where the system currently sits. What this does to strategy when dependency is no longer a supply issue, but a design constraint baked into future planning. Pulling together procurement behavior, industrial bottlenecks, and geopolitical leverage into one structural conclusion. Gallium is less about China restricting exports and more about a global defense system quietly learning it can no longer assume neutral materials. Cold and methodical, slightly more reflective, tighter synthesis, controlled forward-looking tension. At a certain point, the gallium story stops being about trade policy. It becomes something closer to infrastructure realism. Because once you follow the chain far enough, from export licensing delays to procurement adjustments to semiconductor design conservatism, you realize the system is not reacting to a shock. It is adapting to a new baseline where material neutrality is no longer guaranteed. That sounds abstract, but it shows up in very concrete ways. Defense procurement cycles begin embedding supply chain scoring not as an add-on metric, but as a core evaluation factor. Semiconductor firms start treating upstream material geography as part of product design constraints. Governments start funding capacity not just for production, but for redundancy across multiple processing stages. And none of this requires a formal declaration of dependency. It emerges through accumulated friction. China's role in gallium processing sits inside that friction point, not as a total monopoly in the simplistic sense, but as a dominant node in a system where midstream control, refining, separation, and export licensing is enough to influence timing and competence. And in high-performance electronics, competence is not symbolic, it is operational. If you strip the narrative down to mechanics, the key shift is this. Advanced defense systems are increasingly built on materials whose supply conditions are politically sensitive, not just economically optimized. That doesn't mean immediate shortages. It means planning assumptions that used to treat inputs as stable now have to treat them as conditional. And conditional systems behave differently. They hedge, they duplicate, they slow down. Which brings us to the central tension that doesn't resolve cleanly. Efforts to reduce dependency often increase complexity before they reduce risk. Domestic gallium initiatives, allied sourcing strategies, recycling programs, all of them are rational responses. But together, they create a more layered system with more coordination points, more certification steps, and more opportunities for delay. So resilience becomes something that looks strong in policy documents, but behaves like friction in execution. Now, the prediction side of this is not dramatic in a cinematic sense, but it is structurally clear. Over the next cycle of defense modernization, especially in radar, electronic warfare, and satellite-linked systems, material independence will become a design constraint, not a procurement preference. That means engineers will increasingly be asked not just what performs best, but what performs best under supply uncertainty. And that second question reshapes outcomes in subtle ways. Some systems will be delayed. Some will be redesigned away from optimal materials. Some will carry higher costs just to avoid concentration risk, not because gallium disappears, but because its availability is no longer treated as fully external to strategic control. There is also a broader implication that extends beyond gallium itself. Once one material class is successfully used as a leverage point through midstream dominance and export licensing, other materials in similar positions, even if not currently constrained, get reevaluated inside defense and industrial planning systems. That creates a wider psychological shift in global supply chain architecture. The assumption that global means neutral starts to erode at the engineering level, not just the political level. My view is that this is the real turning point people are circling without always naming directly. Not a decoupling event, not a clean rupture, a slow redesign of industrial assumptions under the pressure of controllable bottlenecks. And I'm not fully convinced policymakers or industry planners have fully priced the long-term cost of that redesign yet, because it doesn't show up as a single line item. It shows up as accumulated inefficiency across multiple programs. The doubt I keep returning to is simple. Whether the current push for diversification is actually restoring stability or just building a more expensive version of the same dependency spread across more points of failure. And the prediction I'd leave you with is this. Quietly, without announcement, the next generation of defense electronics will be defined less by maximum performance and more by controlled vulnerability. Not because that's ideal, because that's what the material system now allows without introducing unacceptable risk. If you want to understand where geopolitics is actually moving, don't just watch the headlines on export controls. Watch the engineering constraints they quietly rewrite.